ये स्टार्ट में पॉज करने के लिए पॉज करना ठीक है ये हो गया आते हुए थैंक यू okay, so I'm going to start. For
Okay.
the manual, can you hear me?
Yes, I can hear you.
Okay, so I'm going to start. So today I'm going to be presenting on Montgomery's state correlation conjecture and bound for Montgomery's F function. Okay, so before starting off, I want to give you a sort of an overview so that you know where we are headed. So Montgomery in his 1973 paper introduced a function f. Okay, so this function he was able to estimate for in the interval. This function is defined as two variables, alpha and t, where alpha is a real variable and t is greater than or equal to 2. So Montgomery was able to estimate this function f when alpha lies in the unit in the interval -1 to 1. Okay, so he was able to estimate this function in this interval. But for the for alpha with absolute value greater than 1, this we don't know much about this function. Okay, so Montgomery's function is about the behavior of this function outside of this interval. Okay, so before getting to the Montgomery's theorem and Montgomery's conjecture, we need this lemma, which Montgomery introduced in his paper. So although all these terms might look very intimidating, but just ignore them for now, and we are going to just go through the proof, and all of these terms will pop up very naturally. Okay, so let us start with this Riemann-Konmano explicit formula. So this formula was conjectured by Riemann in his 1959 manuscript. So it was not exactly this formula, but it was somewhat similar to this formula. And what's remarkable about this formula is that on the left we have a partial sum of the Dirichlet series involving von Mangles function, and this von Mangles function is defined for prime powers like this. It's defined to be log t if n is a prime power and 0 otherwise. So you can see this von Mangles function is a weighted function of prime powers, but we can kind of ignore the higher prime power, and we can just think of it as like a weighted function of this prime. Okay. So on the left we have information about primes, and on the right we have information about zeta. This sums involving non-trivial zeros of zeta and trivial zeros of zeta. Okay, and this formula, obviously we want the denominator to be not equal to 0, therefore we want s to be not equal to 1 or non-trivial 0 or non-trivial 0 or -1. And also this explicit formula holds when x is not a prime power, and this has something to do with the fact that von Mangles function has a jump at prime powers. So this formula does not hold for prime powers. Okay, moving on, if we plug in, if we assume our Riemann hypothesis, which means that we can take the non-trivial 0 of the Riemann zeta function to be half plus I gamma. So now the real part of non-trivial 0 of Riemann zeta function is 1/2, and if we take S to be sigma, for instance, sigma plus IT, and plug this into this von Mangles explicit formula, then we get this thing. So we are just plugging these two things. Assuming Riemann hypothesis, we are plugging this rho, and we are taking S to be sigma plus IT. And now we use this famous, well-known result that the logarithmic derivative of Riemann zeta function is given by the minus times the Dirichlet series of von Mangles function. And this relation holds whenever real part of S is greater than 1. So we can plug in this expression from logarithmic derivative of Riemann zeta function into this our previous formula, and we get this. So we just plug in this. Okay. And now what we do is we kind of reflect this formula along the critical line, which means that we replace the sigma with one minus sigma. Okay. So in our hypothesis of the lemma, sigma was assumed to be greater than one. So now we have kind of reflected this formula along the critical line, so it becomes one minus sigma. Okay. And the reason why we do this is because if you see here, we want this, we want kind of spheres in here. So if we take sigma, if we reflect sigma along the critical line, then if we, then this would become half minus sigma. So previously it was sigma minus half. And if we reflect this equation, this formula along critical line, then we get half minus sigma. And now we can add these two formulas, and then we will get squares in the denominator. Okay. So upon, if you subtract the left hand side of 6 from 3, then we get the left hand side to be this 6. Okay, and now we get squares in the denominator. So for instance, if we are clever and we choose, let's say, sigma to be 3 half, then we will get this thing to be 1, and this thing will be t minus the ordinate of the non-trivial zero, non-trivial zero prima zeta function. And this might give us some useful information about the distribution of non-trivial zero distribution along the critical line. So moving on, if we subtract, if we do the subtract the right hand side of 6 from 3, we get this thing, which looks very ugly, but this is just simple algebra. And now, okay, so when we saw the Montgomery's explicit formula, we saw that it does not hold for x equals to prime power. But this thing here is continuous if we keep sigma fixed and vary x. And the left hand side is also a continuous function of x if we keep sigma fixed. So these two are also equal when x is also a prime power, because they are continuous everywhere else. So they must also be equal when x is a prime power. Okay, so we get this, and now the only thing that remains to prove that lemma is that we need to estimate this logarithmic derivative of Riemann function, these two and these two terms. Okay, so we just need to approximate these three terms, and these are pretty easy to estimate. We just use basic algebra and calculate it and stuff. And you estimate this logarithmic derivative of beta using the functional equation of beta. Okay, because we know very well about the gamma logarithmic derivative of gamma function. So using that information, we can estimate this logarithmic derivative of beta. Okay, so we can very easily estimate these three terms, and we get these three estimates, and plugging this into this formula, we get over them. Okay, so what a useful thing we got from this that lemma was that we got a sum over the ordinates of the non-trivial zeros of the Riemann zeta function, and we get something in the denominator which looks useful. For instance, when we plug in sigma equals to 3 half, so then this will be 1, and the other, and we will have 1 over 1 plus t minus gamma squared. And so this gives you kind of a distribution of these ordinates of the non-trivial zeros of Riemann zeta function. So moving on, so Montgomery in his paper defines this function. Okay, so initially one might think this does this function comes out of blue, because like how can someone come up with this function? It doesn't like so, but for the time being, if you just assume and you take this function, and we can note few properties of this function. First of all, this function is real value instead of complex value. Although there are these complex exponentials appearing in the power in here in the sum, but this is a real value function, because if you take the conjugate, you will get this back. Okay, this is real value because if you take the conjugate, you get the function back. And also this is an even function, because again, if you plug in minus alpha, then we will get this in the exponent, we will get gamma prime minus gamma. But because omega is a even function, this wouldn't change anything. the omega is a even function. So this is why that happens in the even function. So one thing that I forgot to mention is that this talk will be very accessible because there is no new definition. For instance, if you are attending the say a talk of algebraic geometry, there will always be so many definitions, but in this talk there will be almost no definition. You just have to use the basic tools of analysis cleverly. So, okay, so this function is also non-negative because we can write it as an integral with an integrand which is non-negative. Okay. So I got this from the people of earlier. Okay, so Montgomery proved the following theorem. Okay, so it gives you an estimate of this f function when alpha lies between 0 and 1. And this, moreover, this estimate holds uniformly if you make alpha stay away from 1. Okay, so we want to get to this estimate. I will just give you the highlight of the proof, the main components. Okay, so as I previously remarked that if you plug in sigma is equals to 3 half, you will get in the denominator here 1. Okay, so and then we can write it like this. We just plug in sigma is equals to 3 half. That's all we do. Okay, and now we know that this whole correct greater than equals to 1 and t any real value. Okay, so we just plug in sigma equals to 3 half in that previous lemma. So we get these two terms left on the left hand side and on the right hand side. Okay, so now Montgomery theorem essentially follows by calculating the mean square of these left hand side and right hand side. Okay, so to calculate the mean square of left hand side, what we do is instead of we just restrict the sum to sorry. So originally there was no restriction on gamma and gamma prime in the sum. Okay, so left hand side was given like this, and there was no restriction on gamma whatsoever. But now we want to restrict gamma and gamma prime to this interval 0 to t. Okay, then we get these other sums as well. Because we are restricting this one, and then we get these extra sums. And so now what we will do is we will approximate these two integrals, the last two integrals, and see what error do we get. Okay. So an essential thing that we need to approximate these two integrals, these last two integrals, is that we require this formula of Riemann, which he also conjectured in his paper. So Riemann conjectured a lot of things in his 1959 seminal paper, but he wasn't able to prove many of the things, which most of the things were proved later on by other mathematicians such as Landau and von Mangold. So Riemann conjectured that the number of non-trivial zeros from up to pi t are approximately t over 2 pi log of t over 2 pi minus t over 2 pi. So they grow like t times log x, t times log t, sorry. So the number of non-trivial zeros up to high t grow like t times log t. We also calculate that there are infinitely many zeros in the critical script. Okay. So Riemann wasn't able to prove this formula. So he was just kind of vague about this formula. He didn't mention any explicit any error term. But von Mangold was able to prove this formula with an error term of log of t. Okay. So if we see this, and what will be the density of the non-trivial zeros in this step up to high t? So if you divide n of t over t, these are the number of non-trivial zeros. If you divide it by t, so we get a density of log t. Okay. So there you go. So because the density is log t, we can expect that the number of non-trivial zeros in a unit interval must be this is big log notation. This is product notation. This is just saying that n of t plus 1 minus n of t is big log of t, which means it's less than or equal to some constant times log. So because due to this heuristic argument, we saw that on average the density of the non-trivial zeros is log of t. So in a unit interval, there must be approximately log of t non-trivial zeros. So that's how we get this thing. So this is not a rigorous proof, but this This is a heuristic argument. Okay. So this is Riemann's original manuscript. So if you see right in the middle, I'm not sure if you can see, but here it's written T over 2 pi log of T over 2 pi minus T over 2 pi. I must admit, Riemann's writing was very illegible. And also it's in German. Okay. So we have this result about the distribution of non-trivial zeros along this critical curve. Okay. So this is also well-known result, and you can find this find a proof of this result in Davenport's classical multiplicative number theory group. And using this result, we can prove this thing very easily. Like if I give you a minute or two, you can easily deduce this thing from here. Okay. Okay. So moving on. Now because we have this estimate for this sum involving the non-trivial zeros, we can estimate, so it can be easily shown that these two estimates are very easy. You can show this very easily using this thing, that the number of non-trivial zeros are at most, or of order of magnitude at most log t. Using this fact, we can easily prove these two estimates, which were appearing in the two integrals of mean square of left hand side. Okay. So using this estimate, you can easily show that the integral of this sum, this integrating looking sum, is of order of magnitude at most log cube t. So this is very easy. You can this involves just simple calculus. Okay. So this involves just simple calculus. And moving on, you can also prove this thing. So this just involves calculus, nothing else. So although one we got an error term of log 3t and the other one log 3t over t, but this this smaller error term doesn't help us because we have to add these two things. So we get an error term of log 3. Okay. So all in all, we get the root mean square of left hand side to be this integral of non-trivial zeros restricted to this interval 0 to t and some error term, which is log 3. Okay. So now what we want to do is we want to extend this integral to the whole of real line. So right now, the integral on the right hand side is on the unit interval, on the interval 0 to t. What? Gamma and gamma prime both are in this interval. Here? Yeah. No, this is not contact. This is different. This integral is different from this thing because this was the error integral that was contributing to the error. So we had this thing. Okay. So we had this main integral and then these two other integrals that we were trying to estimate.
Okay, so you are separating.
Yeah. So we want to estimate these two integrals. Okay. And we estimated them using this result. And we get that these both integrals are of order of magnitude at most log qt. And so we get this result.
Okay, this is the estimation of that one.
This,
of log 3.
so now, although this is log 3t,
Yeah.
3t over t, but this doesn't help us because the other error term was log 3t. So now we are adding two error terms. One is of log 3t, cube t, and the other one is log cube t over t. So altogether, the error term is log cube. Okay. So now we want to extend this integral to the whole of real line. Okay, and see what error do we get. Do we get an error larger than log cube t or smaller than log cube t? And see. Okay. So we do this, and again, this involves. So we want to see what is the error term error we get when we take the integral from t to infinity, and the error we get from when we take the integral from minus infinity to 0 of this sum involving the non-trivial. Okay. Again, using this estimate for the sum of the non-trivial zeros restricted to this interval from 0 to t, you can easily estimate these two integrals. Okay. It just involves simple calculus, nothing more than that. And so we get an error of log Q and log square T. So originally we had an error of log QT, and when we are extending the integral from 0t to the whole of real line, we are getting another error of log square t, which is also smaller, but that also doesn't help us. So we just write it as log square. Okay. So now we have extended the integral to the whole of real line and restricted the imaginary parts of non-trivial zeros to the interval 0 to t. Okay. Now what we do is we interchange the sum and the integral. We can do that because the sum is finite. Because there are only finitely many non-trivial zeros in the interval 0 to t. Okay, so we can interchange the sum and integral. And we can evaluate the integral. One can easily evaluate the integral using, let's say, Cauchy's gravity unit formula. And we get this thing. So now one start to see where the Montgomery F function emerges from. Okay. So now we have estimated the root mean square of left hand side. Now we are going to shift to the root mean square of right hand side. So what's the time? I'm doing time. So okay, so yeah. So right hand side was given like this. Okay. So what we are going to do, the strategy is instead of estimating the root mean square all at once, what we are going to do is we are going to estimate the root mean square of this term, root mean square of these terms, all of these individual terms. Okay, we are going to estimate the root mean square of each of the individual terms. Okay, so for instance, if we want to estimate the root mean square of this term, x to the power minus 1 plus it times log of t absolute value of t plus 2, then you can easily estimate this mean square and you get this thing. Just simple calculation. Okay. This is very simple integral. It just takes the square and so. Okay. And similarly, we estimate the mean square of the other two terms, this term and this term. But this term has x to the power minus 1 plus I with it. Okay. So we can also estimate the mean square of other two terms very easily. Just simple calculus. Okay. To estimate the mean square of this this first term is the sum business. Okay. So now we want to estimate the root mean square of this term. Okay. We can write these two sums as a single sum. Okay. And now this is a Dirichlet series on the imaginary axis. So we can just combine these two sums into just one Dirichlet series where AXN is given like this. Okay. So far, you can just combine these two things. And now we have a result of Montgomery and Vaughan, which says that you can estimate the mean square of Dirichlet series like this on the imaginary axis. Okay. So using this result of Montgomery and Vaughan, we are going to estimate the mean square of this monstrous term. Okay. So this is just applying the Montgomery Vaughan. Okay. Just simply applying it, nothing else. Okay. And then if we move on, we get four terms. See, we get four terms. There are two kind of main terms and two error terms. Okay. So now we are just down to estimating these terms involving fundamental functions. Okay. If we can somehow estimate these terms involving fundamental function and these partial summation of kind of like not some these terms involving fundamental function that we are done. Okay. But we can do this very easily using Abel summation. Abel summation is a tool that is built specifically for this purpose, where you have one function that you don't know, you have like product of two arithmetic functions, and for one function you know something about the partial sum. So we know what partial summation of partial sum of fundamental function looks like. It's a Chebyshev function, and we know it's let's say it's O of x. So using this Abel summation, you can estimate these sums involving fundamental and we arrive at this nice looking estimate. So we just estimated the sum using auto summation method, which is a very basic, when you start first, take a first course on analytic number theory, you learn in probably first or second lecture, the auto summation. And we get this, okay? So now we have estimated the root mean square of each of the individual terms. Okay, but now how we can relate it to the root mean square of the original term. So you see, here we had r of xt given as like this, and we had the four terms, and we have now estimated the root mean square of each of the individual terms. And how can we relate it to the root mean square of this right hand side? So for this, we have this lemma. Okay, so it says to estimate if you have information about the root mean square of each of the individual terms, what you need to do is you just take the term with the highest root mean square, and then take the term with the stacking highest root mean square, and then the error term is given by the square root of their product. And this is very simple, and you just get it using. This is a simple application of Cauchy-Schwarz inequality for integrals. Okay, so now we know how we can relate the root mean square of right hand side to the root mean square of each of the individual terms. But so now we need to know which term dominates. Okay, root mean square of which term dominates. Yeah.
Yeah, one question, why and what about the other values of n? So it only depends on number and.
Yeah, only terms on the first two largest root mean squares.
Doesn't depend on the.
No. Yeah, it doesn't. So now we need to know like which those terms root mean square dominates. Okay, and then we analyze that the root mean square of different terms dominates in different regions. Okay, so for instance, if we take the region x greater than or equal to 1, less than or equal to log t to the power 3/4, then the root mean square of m1 xt, which was this monstrous term, the root mean square of this monstrous term dominates, and the all other and the root mean square of all other terms is small o of t over x squared log square t. Okay, so these are like these are much smaller compared to the root mean square of this main monstrous. Okay, so we get this. Okay. And then if we choose this range, if we now suppose that x lies between log of t to the power 3/4 and log of t to the power 3/2, then we see that all of the mk's, all of the root mean square of all the terms is small o of t of log t. Okay, so then the root mean square is also small o of log of t, because the main term is o small o of log of t, and the other two more terms are also small o of log of t. And using this previous lemma, we get this too. Okay, and then finally, if we restrict x to this range, when x is greater than log t to the power 3/2 and less than or equal to t over log t, then the final, the root mean square of the final term dominates, and the root mean square of all the other terms is small o of t of log of x. So you see, this is like small o of t of small o of the main term of the root mean square of the term. Okay, and then using this previous lemma, we get this. Okay? So nothing complicated about that. Okay, finally, how can we write this as a sum? So we saw that in different ranges, we get the root mean square to be this thing in different things. But how can we write it as a sum? So now I'm saying that if you take x to be greater than 1, less than or equal to t over log t, now I'm not caring about these individual ranges. I'm just writing it as a sum. You see, I'm writing the sum of this, and this. I can do this because when I restrict to each of the individual ranges, the other terms kind of get engulfed into the error term. You see, So the other term kind of gets engrossed into the arrow term and we get the same thing. So for instance, if you restrict x to be x greater than or equal to 1 and less than or equal to log t to the power 3 over 4, then you can see that t of log t is small of t over x squared log squared. So this kind of gets into the arrow term of this. No, not necessarily. Even there's a second point here, but just I'm kind of ignoring it. But you get the point. We can write it as a sum because the other terms I'm getting also is the arrow term of the relevant term. That's it. Okay. And now the final step, what we do is we replace x by t to the power alpha. And we can do this because we only prove this thing when x is less than or equal to t over log t. And we know that t to the power alpha is also a small log t over log t. Is much smaller than t over log t. T to the power alpha when alpha is less than 1 is much smaller than t over log t. Okay, so then we can use this formula. Okay. Just replace x with t to the power alpha, and we get this. And then now equating the root mean square of the right hand side and the left hand side. Again, also substituting x equals to t to the power alpha in the mean square formula of left hand side, we get this thing. And you now kind of see that the Montgomery set function is kind of present here. So now you see it kind of naturally pops up. Okay, and now equating these two, we get the Montgomery result. So you see there was nothing technical except just Montgomery small inequality. That was the only maybe slightly technical result. And the other than that, it was usual analysis. Okay, so Montgomery, after some years, refined his result by improving the arrow term, and he proved this result. Okay, so if you go back, in the Montgomery's result, we had error terms appearing as O of 1 as well. Yeah, so if you see, we also have an error term which is O of 1. Okay, but then later Montgomery improved this and got an error term of O of square root of log t over t log t. Okay. Yeah, and now and this holds uniformly for alpha greater than equal to 0, less than equal to 1.
But that was small.
Sorry?
That was small.
It is also small of 1. No, although it is big O of this thing, but it is also small of 1. Because this thing goes to 0. This thing goes to 0, so this is also small O of 1. But now we know precisely kind of what the arrow term is. We have more information about the arrow. Okay, so now this is what holds uniformly when alpha is greater than equal to 0, less than equal to 1 in the unit interval. Previously, we knew that the result holds uniformly when alpha is away from 1. There was like alpha less than equal to 1 minus epsilon. Yeah, in the Montgomery's original result. But now we know that it holds uniformly when alpha is in the unit interval. Okay. So how can we use the Montgomery's theorem? What is it good for? So Montgomery proved this another lemma, which kind of relates the weighted sum of pairs of non-trivial zeros, yeah, to the behavior of Montgomery's F function. So on the left hand side, we have kind of a weighted sum of the pairs of non-trivial zeros, or in this imaginary part of non-trivial zeros of the function, and to the right we have Montgomery's F function appearing. But we also only know the behavior of f and alpha lies between -1 to 1. In the theorem, we saw that we knew the behavior when alpha lies between 0 and 1, but because it is even, so we know the behavior when alpha lies between -1 to 1. So if we can kind of pick some function whose Fourier transform is just supported on the interval -1 to 1. So yeah, this is the notation for Fourier transform. So the condition is that R must be an integrable function and this Fourier transform must also be integrable. So if we pick a function whose Fourier transform is supported on the interval -1 to 1, because then this integral will be over this interval, and we know the behavior of function in this interval. Then we can extract useful information from Montgomery's theorem. So that's what we do, and picking clever choices for this or we get interesting results. So one interesting result that Montgomery here gets is that more than he proves that the number of simple non-trivial zeros, simple I mean that the order of the zero is one. Okay, so the number of non-trivial simple non-trivial zeros up to height t is greater than or equal to 2 over 3 plus 4 small of 1 times capital N of t, which is the number of non-trivial zeros up to height t. So which means that more than 66% of the non-trivial zeros of beta are simple. Okay. So this is a very interesting result. This is an unconditional result. Like he doesn't assume anything else except the Riemann hypothesis. Okay. And now Montgomery arrives at another very interesting result, and he predicts kind of the behavior of f function beyond this interval. So as I remarked at the beginning, that we know the behavior of this function, Montgomery's f function when alpha is lies between -1 to 1, but Montgomery using some heuristic argument conjectured the behavior of f when alpha does not lie in this interval. So which is precisely the Montgomery's conjecture. Montgomery conjecture says that if you assume the Riemann hypothesis, then f of alpha is 1 plus O of 1. It's like goes to 1. And moreover, if you assume that you are in the bounded interval, in a compact interval, then it converges this estimate for uniformly. It means that the constant does not depend on alpha. Okay. So this is sometimes called the strong Montgomery state correlation conjecture as well, because we will see that using this conjecture we can get another interesting conjecture. So which is usually called the pair correlation conjecture. Sometimes this is called just the Montgomery conjecture, and the other one is called the Montgomery pair correlation conjecture, and which is given like this. Okay. So we saw earlier that the number of non-trivial zeros up to a height t are almost t times log t. Okay, t over 2 pi times log t. So it means that the average spacing between the non-trivial zeros are 2 pi over log t. Okay, the average, because it's t over 2 pi log t, so the average spacing is 2 pi over log t. So now what we are doing is we are taking the pairs of ordinates of non-trivial zeros of Riemann beta function up to height t, and we are imposing the restriction that these that their difference or distance is less than or equal to some constant times average spacing. Okay, some constant beta times average spacing, and Montgomery conjectured that it's asymptotic to t over 2 pi log t, which is the number of non-trivial zeros, times some factor which depends on beta. Okay. So using this conjecture, we can prove another interesting result about
This conjecture is not depending on.
it actually is. I think I forgot to mention. Yeah, I forgot to mention it actually. Assuming Riemann hypothesis. Yeah. So assuming Riemann hypothesis, we conjecture that this thing must hold. Using this conjecture, we can prove this thing. And this thing follows because you can see that you take any beta, you take any positive beta, then the number of non-trivial zeros, pairs of non-trivial zeros whose spacing is less than 2 pi beta over log t is infinite. Because the thing on the right hand side is goes to infinity as t equals to infinity. So the number of pairs of non-trivial zeros whose distance is smaller than 2 pi is smaller than beta times average spacing is infinite. Okay, so which means that we have infinitely many pairs of conjective non-trivial zeros whose difference is less than beta times average spacing. But we can replace this average spacing by 2 pi over log gamma n. Because log gamma n, 2 pi over log gamma n is greater than 2 pi over log n. Let me take a look. So that's what should be that. Important. So this conjecture says that the number of pairs of non-trivial zeros of Riemann zeta function, which differ by beta times the average spacing, is infinite. There are infinitely many such. Yeah. So if we take gamma n plus 1 minus gamma n, okay, these are conjective non-trivial zeros. Okay, so this spacing must be smaller than this one. So this is less than 2 pi over beta times log t, 2 pi over log t. But because gamma n lies in this interval from 0 to t, therefore log of 2 pi over this thing is greater than 2 pi over log t. Okay, and so this thing is less than beta times 2 pi over log of. Okay, so I take this over here, log of gamma n over 2 pi is less than beta. Okay, so there are infinitely many consecutive non-trivial zeros which differ by beta. And beta can be chosen to be any arbitrary constant. So it just means that the limit is zero. Okay, so next, assuming that a correlation conjecture, one can show that the number of simple non-trivial zeros is greater than or equal to 1 plus small o of 1 times t over 2 pi log t. So that the other result of Montgomery, which showed that more than 66% of non-trivial zeros are simple, was unconditional. It assumed Riemann hypothesis, but there was nothing else. Okay. So now, if you assume this paired correlation conjecture, you can show that almost all the non-trivial zeros of beta are simple. Okay. Not all, almost all, which means that like percentages infinity in probabilistic. Okay. So although like in the interval from -1 to 1, we know the function very well. We know the estimate. We know the estimate. But outside of this interval, we don't know much about this Montgomery step function. Although this Steve Gonek, Goldstein, Oslook, and Snyder were able to prove a partial result in this direction. Actually, Gonek was a student of Montgomery. So they actually proved that this Montgomery step function is bounded below by t over 2 pi, t over 2 minus alpha, when alpha lies in this interval. So if I draw this picture, so it says that something like this. So here is 1. So we want to know the behavior of Montgomery step function in these intervals. Okay. So it just states that the Montgomery step function is bounded below like this from this. The original conjecture is it is all 1, like as t approaches infinity equals to 1. But they showed that it is bounded below by this thing. We want this thing, but they showed that this is bounded below the this kind of 1. Okay. So there are also many equivalent forms of pair correlation conjecture. One was introduced given by Gallagher and Mueller, and the other by Daniel Goldstone. Goldstone, actually, I'm going to show you what was the equivalent form of the pair correlation conjecture by Goldstone, and the one was given by Gonek, Goldstein, and Montgomery. So this last one was something about estimating the second moment of the logarithmic derivative of Riemann zeta function. Okay. And the one which was given by Goldstone is of interest to us. And he showed that if you can kind of show that the average of Montgomery stack function is asymptotic is one for any beta, for any B and for any L, then this is essentially equivalent to the pair correlation projection. Is that clear? So you take any beta, like no matter how far you go along the line, and you take any length L, then the average must go to one. If we assume the calculation conjecture, then it's easily possible. Nothing, if the function goes to one, then the average must also go to one. But if we know that the average goes to one, then the function should also go to one. This was proved by Schwarzman. And although like proving this is very difficult and there hasn't been much progress, but we were able to, by we, I mean, Emmanuel and his group, were able to prove, get some good bounds on this average of Montgomery stack function. Okay, so they showed that if you take beta to be b to be any b to be greater than or equal to one, and you take L to be large. By large, I mean like L depends on beta, and whenever L is greater than or equal to, let's say, L which depends on beta, then we have these bounds. Okay. So previously these bounds were known to be just 1/3 and 2. So here it was 2 and here it was 0.33. So these bounds were significantly improved by Emmanuel and along with Montgomery, Conjecture, and Montgomery knowledge. Okay. Okay. And then Emmanuel was also able to improve these bounds once again in 2023 along with Montgomery knowledge and Ramos. So now, although like you see, this is very, you might say it's very small improvement, but it involves very different framework. Okay, it involves framing the problem in a very different way. Okay, so how are they able to improve these bounds to improve significantly these bounds from 1/t to 0.9278 and 2 to 1.6302? So Carnival and his group were using the technique of Fourier optimization. Okay? So although like I'm not going to go into this technique and how it's employed to get these bounds, but I'm just going to give you the main idea behind the Fourier optimization, what we are doing in Fourier optimization. So the main idea is that we have some problems. We have some like class of functions. Let's say function which are integrable to Fourier transform, and let's say band limited, it has a compact support, and to Fourier transform is let's say non-negative or less than or equal to 0 or something like this. So we have some class of functions with some prescribed conditions on them, and then we want to kind of optimize some quantity which depends on those functions. Okay, and the main idea is to get like get the estimate supremum or infimum of that quantity, which ranges over that class of functions. Okay, so if you get so that's what Emmanuel did in his paper, that he was able to optimize something, get a good estimate for the good, optimize some quantity which are varied over this class of functions, and using that he was able to improve his points. And we are going to explore how he was able to do that, and moreover the limitations of the technique and some plausible approaches in my actual lecture. So I think that's where I'm going to end here, and thank you. Emmanuel, can you hear me?
Yes, I can hear you.
So any questions?
Want to. You want to improve these boundaries?
So that I cannot say.
Starting.
Yeah, so that would be a very ambitious target. Yeah. So improving these bounds, but one can certainly look into like what can one like what restricts one from improving these bounds, like why the techniques cannot be used further to improve the bounds or something like that. Along those lines.
Because as you mentioned that next target is like to study that proofs in detail how these
Yeah.
transformations are involved.
Yeah, how the portfolio optimization technique works, yeah.
This is the next target.
Yeah. Yeah, so I'm going to like read these papers in much more detail and try to see like, how we found, well, like, are there any possible approaches which one can use to kind of improve these forms? Maybe one kind of changes the class of functions.
Or maybe we say that this cannot be.
Yeah, that would also be a very ambitious target, like, it would have been long done by manual, like it. So Emmanuel, do you have any questions?
If I heard the question, I mean, I cannot hear very well what they are speaking in the room. I mean, I can hear you. I can hear you fine, but
So like my other course provider, ma'am, Shaheen was asking me what you are going to do next. Like, so I was explaining to her that I'm going to study this technique of Fourier optimization and see, what are like limitations of these techniques and whether one can, kind of, just like you did in your paper that, you change the class of function, like, the one that was introduced by LP, and then you kind of got better estimates for the bound. So maybe see if one can maybe change the class of functions and that will lead to the improvement.
yes, I think there are a few possibilities to be looked at in this subject. I have hopes that this lower bound can be improved to something closer to 1, which is the true expected value. As the upper bound should be a bit harder because there is some genuine obstacles in the middle. But I mean, of course, in a first step, you would be looking at the paper, trying to learn these techniques, trying to learn. I mean, this is also useful in other problems in number theory. So just by reading this paper and studying this material has a lot of value. And then we can start taking a look at these lower bounds to see if we can find a way to look at this problem from a different angle and get something better than what has been done before. That's my hope.
Yes, yes, like I attended your talk that you gave for some conference, I think that was in like Brazil, that online conference, and you use the same technique of Fourier optimization to get some estimates for quadratic forms or something like that, like, I'm not sure, no, I kind of forgot.
Yes.
Yeah. So Amanda, do you have any suggestions or anything else, any comments?
No, I mean, I don't have any particular questions, I mean, to you in front of the audience, maybe we can start working on this. I liked your presentation in general. I would have started maybe a little less technical, in the first slide, you were already bringing in the heavy machinery. I would just make a switch, maybe start talking about the Riemann hypothesis first and how this pair correlation, the Riemann hypothesis is a statement about the horizontal distribution of zeros, right? How are the zeros horizontally distributed? And the answer is that they should all be aligned, so there's just one point. So they are trivially horizontally distributed. And then the pair correlation comes after. It's a question about the vertical distribution of zeros. Once you know that they are aligned, how are they distributed vertically, And this is what the pair correlation conjecture and this function f alpha tries to answer, So maybe if you're gonna give this talk again to an audience, you might wanna switch some of the stuff that you showed in the middle and maybe bring it a little bit to the beginning, I think to motivate a bit better before start talking about the more technical part. But overall, of course, it's perfectly fine.
Yeah, but the audience is familiar with all the background because the last talk I gave what's all about this background stuff like Riemann hypothesis and this functional equation, and the same audience is here right now.
This is something that all students have in common, you know. When you are a student, and I was the same thing. You get very excited with technicalities, and you try to show people in 50 minutes what took you 3 months, 6 months to understand. I say, once you get older, your talks will become less and less technical to a point that you just have some bullet points, and you're just gonna talk about vaguely about stuff and so on. And eventually, if people want to see the technicalities, they will look at the paper or the thesis.
Yeah, I agree.
That's true. We started with.
But I think I
With the
really
jump.
appreciate your ambitious approach. I really appreciate it. It was very ambitious.
I guess, that's all maybe perhaps. So. Let me. So I hope maybe we will try to meet maybe next week or something, or to discuss what I have read so far.
You're talking to me?
Yeah.
Okay. Next week I will be traveling. We can talk early the week after. Okay, on the 26th, 27th, if that's okay by you.
Yeah, that's completely fine for me.
Okay, and
Yeah.
then you give me the updates on your applications as well.
Yeah. Thanks for your precious time, and thanks for taking the time.
All right,
Thank you, Professor.
it was nice seeing everyone. I hope to be visiting you guys sometime soon, maybe this year or the next one. Okay.
Yeah.
So
Okay. Bye. See you.
I'm gonna be heading to lunch now. See you all. Bye, Atif. Good
Bye.
job. We're talking about 10 days, okay?
Okay. Thank you.
Okay. Keep reading this paper.
Okay.
Till then. Bye-bye. Take care.
Bye.